Hello and welcome. For this video today we are going to look at making ammonia, but we're going to look at the higher tier content and the kind of stuff you need to know that will help you understand the conditions that we have in making ammonia. We've already gone over how the process actually happens and how ammonia is made, and we left the last video on this with a diagram that looked like this. I'm not going to go through this in any depth because there's it's been done already in another video, but basically we have nitrogen and hydrogen combining in a reaction vessel to produce ammonia that is a very useful substance. Now what we're going to look at is an explanation for why we have these conditions in order to make as much ammonia as possible. And if we look inside the reaction vessel, we can see that we have our nitrogen gas, our hydrogen gas, and our ammonia gas, which is actually in there as the reaction goes backwards and forwards. But the first thing to think about and in fact remember is that when we start the reaction off, when we mix the nitrogen and the hydrogen in order to start this reaction, you can imagine that we have high levels of nitrogen and hydrogen and very low levels of ammonia. But as time goes on, we start getting higher levels of ammonia and lower levels of nitrogen and hydrogen. And in fact what happens is we reach a point where the amount of ammonia that's being produced is exactly the same as the amount of hydrogen and nitrogen being produced. The rate of reaction in both directions has reached what we call equilibrium, and that means that the reactions occur at the same rate in each direction. So the ammonia is being produced at the same rate as the nitrogen and hydrogen, and what we really want to do is actually make sure that we get as much ammonia being produced as possible, and we want to encourage the forward reaction as much as we can. And the first thing to look at is this idea of pressure. One of the conditions in the reaction vessel was to have a high pressure, 200 atmospheres we said, and the reason why we have that is as follows. Now imagine I've got a syringe here full of nitrogen and hydrogen, which is happily reacting to make our ammonia. You can imagine at some point we reach equilibrium, and if we just have a look inside to see what's going on, we have our gases, nitrogen and hydrogen and ammonia, and they are happily reacting in each direction. But what we could do is actually increase the pressure inside there. So if we pull the plunger down, we have a much higher pressure inside there, and if we now looked inside, we would see that the molecules are much closer together, and this in fact will encourage or increase the rate of reaction in the forward direction. But why does it increase the rate of reaction in the forward direction? Well, that is because that increase in pressure favors the direction of the reaction that produces the least number of molecules. Okay, so if we look at this equation here, we can see that we've got 1 molecule of nitrogen gas and reacting with 3 molecules of hydrogen. So we have on this side 4 molecules reacting to produce, over here we've got ammonia, but we've got 2 molecules of ammonia, so we've got 4 molecules reacting to produce 2 molecules. So here we say that, here we can see that an increase in pressure favors the direction of reaction that produces the least number. The least number is the 2 ammonia molecules, so this increase in pressure favors the forward direction. So in other words, we are going to get more ammonia produced if we increase the pressure, and that is the reason why we increase the pressure for this industrial process. The next condition that we looked at was this idea of temperature, and this has an effect on the reaction, but what we do have to remember is the following. So for our forward reaction going from nitrogen and hydrogen to ammonia, the forward reaction is what we call exothermic. That means it gives out heat to the environment, heat energy to the environment. The reverse reaction is endothermic. That means it takes in heat energy from the environment. So if we have a higher temperature, the endothermic reaction is increased. So in our reaction vessel, if we raise the temperature, the endothermic reaction is increased. In other words, going from ammonia to nitrogen and hydrogen, that reaction is increased. And if we have a lower temperature, the exothermic reaction is increased, and in this case the exothermic reaction is the forward reaction. So if we have a lower temperature in our reaction vessel, that means we have a higher yield of ammonia produced. And this is quite important to remember when we're talking about the conditions that we have. But there is a little twist here in terms of thinking, well, we have, if we keep a low temperature, we can have a high yield of ammonia, so we carry out the reaction at a low temperature. You might have to look at a graph that looks like this, or you may have seen a graph that looks like this. We've got pressure along the bottom versus the yield of ammonia along the side, and this is data for different temperatures. So here we said a lower temperature gives you a high yield, and that makes sense because look, this is our 200 degrees, that's the lowest of our temperatures, and it's giving us quite a high yield of ammonia in comparison to the others. If we have a higher temperature, 500 degrees, we've got a lower yield. But that might make us think, well, let's carry out the reaction at 200 degrees because that's when we get the highest yield. But what you have to remember that is that yield and rate of reaction are two different things. So while we might have a higher yield, we have a lower rate of reaction. So this reaction is going more slowly because of the low temperature, but we're getting a higher yield. So what we want to do is actually increase that reaction rate, but we will have to sacrifice our yield. So right at the bottom here, we've got a lower yield, but we've got a much faster reaction. So what we might do is actually not go all the way up to the highest temperatures or the very highest temperatures. We might use a temperature that is actually some level of compromise in between here, and we actually use a temperature that's around about 450 degrees, and that is because it gives us a decent rate of reaction, but we do sacrifice a little bit of the yield. So what we've done here is we've compromised between the rate of reaction and the yield in order to give us what we think is going to be the best rate of reaction or best rate of production of our ammonia. Okay, so that's a little tricky point that you've got to remember, and this slide here is probably quite an important one for you to make sure you get a grasp and an understanding of why we have the temperature that we do. I've got a little summary slide right at the end which includes all this stuff, so you can have a look at that as well if that helps. Now the next thing to look at very briefly is our summary slide, in fact, and when we're answering a question about the correct conditions for producing ammonia, this is some tips here that I've put together that comes up often when we're looking at exams and what the examiners say. The first thing is to make sure you don't confuse rate of reaction and yield. These are two different things, as we've explained on this previous slide here. If you write an answer and if it comes up as a 6-mark question, this would be quite good, I think, because there's lots you can talk about. But a good answer for this includes how the temperature affects the yield of ammonia, and the way that happens is as follows. We know that a low temperature will give us a high yield but a low rate of reaction, and a high temperature will give us a lower yield but a higher rate of reaction. So our temperature that we use is a compromise between yield and rate of reaction. The second thing you should talk about is how pressure affects the yield of ammonia, and for that one we have a low pressure which gives us a lower yield and a lower rate of reaction, but a higher pressure gives us a higher yield and a higher rate of reaction. Why is that? Well, for this reaction it favors the reaction that produces the least number of molecules, and for our reaction here we said the least number of molecules is our ammonia, so it favors the forward reaction. Okay, so this is a bit of a summary of how you might talk about optimizing the conditions for the production of ammonia, and these are the key things to talk about. And one thing I would say is that if this question comes up, this question is notorious for students writing lots and lots and lots of stuff but actually not getting to the point and therefore missing out on marks. What I would say to you is if it comes up as a big question or a 6-mark question, I would say you separate out into temperature, how that affects it, and those are the points in blue, how the pressure affects the yield of ammonia, and that's the stuff in purple, and also talk about this stuff here about favoring which reaction is favored. Okay, so that breaks it down nicely and explains it quite clearly. Of course, you can add the stuff about the catalyst as well. Now, there is one more thing that I want to go through, because the spec says we're not just talking about ammonia, although that is a big example that we talk about. It does also ask you to describe and evaluate the effects of changing the conditions of temperature and pressure on a given reaction or process. So it might not be ammonia that you're talking about. Here's another reaction that I've given you some information about. This is the equation for that reaction. So we have nitrogen dioxide in a reversible reaction to produce this substance called nitrogen peroxide, sometimes called I think dinitrogen tetroxide or something like that. But either way, I'm sure they'll give you the name of it in the exam. But we have some information here. The forward reaction is exothermic and the reverse reaction is endothermic. So if I was to give you a couple of quick questions about this, let's say we had a high temperature. What would happen if we had a high temperature? Well, that's to do with which direction is exothermic, and we can see that the exothermic direction is the forward. The exothermic reaction is the forward reaction. Let's have a look back here. We said that a high temperature would give us a lower yield but a high rate of reaction. Okay, so in this case, a high temperature will give us a low yield but a higher, I'm being lazy now, higher rate of reaction. Okay, so that's what would be the effect of having a high temperature. If you wanted to actually increase the rate of reaction, so if you wanted to increase the yield, you could actually lower the temperature. You'd get a higher yield, but you'd get obviously a slower reaction. So you've got to decide for this reaction where you'd actually want that based on some data that you might get. What happens if I have a low pressure? Well, we need to look at the number of molecules reacting on both sides, and for this one, just to make it slightly easier, I've drawn it out. I've got 2 molecules on the left over here, because I've got 2 NO2, and I've got 1 molecule of our nitrogen peroxide over here. So if we had a high pressure, the forward reaction would be encouraged, because these particles are encouraged to be very close together and therefore more likely to react. But we haven't got a high pressure, we've got a low pressure, so that means it's going to be the reverse reaction that's going to be increased, simply because nitrogen dioxide molecules would be further apart in a lower pressure, and therefore the forward reaction would not be encouraged. Okay, so lots to digest and take on board there. I think probably this is an important slide for you just to get under your belt, but the rest of the video obviously explains why we've got this here. Anyway, so that's the video for equilibrium, rates of reaction, Haber process, and so on. That's me done for this one. Thank you for watching, and I'll see you again soon.